Hi, everybody. I have two ideas about making a better rock, paper, scissors AI. The first idea is using a meta strategy. So let's say you have a get move method that represents some particular strategy. Delete, or don't delete, but cut the contents of your get move method and make a method called strategy 1. And then implement a totally different approach and make a method called strategy 2, and so on. So you can have a bunch of strategies. And then what your actual get move method will do is your get move method is going to switch between which strategy you actually want to play depending on how well it's doing. So you'll keep track of, like, have you been winning games recently? And you might just start by picking a strategy at random, and you're always going to play like your strategy 3 or whatever. And as long as your strategy 3 is winning, don't mess with it. But then if you notice that your strategy 3 is losing more often than it's winning, then you'll switch which strategy you're using. So you might have a variable that controls like which strategy are you currently enacting. And then if you detect that you're losing in the last 10 games, if you're losing more than you're winning, then you'd change that variable so that you'd be using your different strategy. So that's kind of the first idea, a meta strategy. The second idea is something called a Markov model or a Markov chain. Here's the idea of a Markov chain. I'm going to use a comparison with your strategy that you already have. Let's say this is your opponent history of play. Let's say they do like rock, paper, rock, paper, rock, paper, rock, paper. So let's say that the strategy that you're using is you're counting how many times have they done rock and how many times have they done paper. And so here rock is 1, 2, 3, 4, and paper is also 4. So you know they've got a 50% chance of playing rock and a 50% chance of playing paper if you're looking kind of statistically at the entire history of their play. The problem is, if they've just played paper, you as a human being know that there is no mystery about what's going to happen next. They're definitely going to play rock next. But if you're just looking at their overall statistics, you're ignoring the fact that what they're most likely to do next depends more heavily on what they've done recently than it does on what it depends on what they did like 100 moves ago. So the idea of a Markov chain is going to be based on probabilities. But you're only going to look at the most recent things they've done to determine what they're most likely to do next. And so that's what I'm just about to explain. So let's say your opponent moves look like this. Let's say they do rock, paper, paper, rock, scissors, scissors, rock, rock, paper. So what you're going to do, let's make an assumption. Let's assume that their next move only depends on the one previous move that they did. So what you can do is you can build up a table with some probabilities. So if their previous move was rock, we want to know what's the probability of each of the 3 possibilities that would come next. And if their previous move is paper, same thing, and scissors, same thing. So actually here, let me do it this way. Okay, so if their previous move was rock, let's count. So here they've done rock, 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 rock. So here I've seen they do paper 1 time after rock. Here they do scissors 1 time after rock. Here they do rock 1 time after rock. So based on our play so far, if they played rock, it seems like they're equally likely to play any of the moves as their next move. So we haven't seen any pattern for what they do after rock. Okay, what about paper? So paper is here, here, here. So rock, paper, scissors. So after paper, we've seen them do paper once. We've seen them do rock once. And then we don't know what they're going to do here. And we've never seen them do scissors. So we would predict that after playing paper, they're 50% likely to play rock and 50% likely to play paper again. So that's the idea. just like your previous strategy, where you're keeping track of how frequently do they do each of the moves, you're doing that same thing, except you're keeping a separate set of probabilities depending on what their previous move was. So if they did rock, here is the probability distribution for what we expect to see next. Or if they did paper, here's the probability distribution for what we expect to see next. And that idea is kind of the heart of a Markov chain. So what you want to do is you want your AI player to have a simulation of what you expect your opponent to do so that you can use it to predict what they'll do, and then you're going to move to beat your prediction of what they're going to do. So that's what all of these probabilities are about. Inside your player, you've got these tables where you saw, okay, so like last round, they played paper. So now you look at your probabilities that are based on the history of your play with this opponent, and you say, all right, so like if I look at all the times they've ever played paper, I know that 70% of the time after playing paper, they play rock. And like 20% of the time they play paper again, and 10% of the time they play scissors. So this is going to be your simulation of your opponent. It's a statistical simulation based on how likely they are to do certain things after playing paper. So what you're going to do is you're going to generate a random number, and you're going to figure out based on your random number which of these things are you predicting they're doing this time. Because just because they're most likely to play rock doesn't mean they play rock every time. So you want your random number to predict like 70% of the time they're doing rock, but 20% of the time they're doing paper, and so on. So you generate your random number. Your random number you use to predict what do you think they're going to do based on their probability distribution. And then you move to beat whatever you predict they're going to do. That's the idea of a Markov model. Just as a quick note about how that might work, when you generate a random number, it's in the range from 0 to 1. So let's say R is the probability of rock, and P is the probability of paper, and S is the probability of scissors. So you can imagine rock, let's say rock is 0.5. So you can imagine it as taking up that amount of the interval. Let's imagine paper is 0.4, and let's imagine scissors is 0.1. So 0.4 and 0.1. So you know that your random number is going to fall somewhere in this interval. So all you need to do is use if statements to test, did it fall in the interval that it's 50% most likely to hit, which is the rock interval, or did it fall in the paper interval, or did it fall in the scissors interval? So you generate your random number, but then you use your variables for the probability of different moves to figure out which of these intervals did your actual random number fall into, and that's your prediction of their play. Okay, so that's the basic idea, and that idea might not seem very powerful, because is it really realistic to think that a good player is going to base their next move only on their previous move? Like, surely it's based on like their previous move and also whether or not they won. Right? That seems intuitive. But this same overall approach can be used to make predictions using any amount of state information from previous rounds. So you don't just have to look at, did they play paper? You could make probability tables based on whatever state you want. So you could look at like when they played paper and won, and when they played paper and lost. And each one of these scenarios is going to lead to a different set of counts. Obviously, it's going to take you a long history of play to build up enough data to be able to know, like, oh, when they play paper and win, they're most likely to do this thing next. Like, you have to play a whole lot of games before you've seen enough examples of them playing paper and winning in order to have an informed decision. But my point is that you can make these probability tables based on any information you want. So you could look at like what were the last two moves and whether or not they won. Or you could look at Like, what do they do when they win and they win? Like 2 wins in a row. Do they switch moves or do they stay the same? So there's like a lot of different, variations on this basic idea that you could choose to explore. Just another kind of practical issue. Probably the best Markov chain approach is going to involve multiple pieces of information, like what was their previous move and also did they win or not. And as I just said, it might take a lot of play history in order to build up enough data to make your predictions. But like, what should you be doing during that play history? Before you've built up enough data to make informed predictions, like you got to be using some strategy. So I like the idea of having your Markov chain strategy, but you only start using it after you've built up enough data. And you have a simpler strategy that's not based on this that you use to gather all the data before you switch over. So I think that's the entirety of my advice for you. Good luck.